Right. First of all, I want to thank you for the organizing committee, Professor, Chairman, Professor Choi, for I'm one of the luckiest one I can. That's one of the international participants. So you can also see my background that I have a picture of the beautiful waterfall of Jeju just to prove that I'm here. Right. Okay. So let me. My topic is about halogen bond induced fluorescent material. Halogen bond is probably one of the most studied non-covalent interaction in the past 10 years. There are all kinds of applications from biochemistry to catalysis. I would say material science probably have the largest number of applications. And of course, I think there's a fundamental interest in terms of understanding the nature of halogen bond, finding the right force field to model halogen bond. So my talk is mainly focused on the material science application. There are many of them. For example, liquid crystal, molecular recognition, magnetic material, theme. So I'll talk a little bit about optical properties application, and also I think very fundamental on supramolecular chemistry and molecular regulation. So I'm not sure whether you're familiar with halogen bond. I will just say a few words on halogen bond, followed by two topics. One is about, that's where I started in the interest in fluorescent material, because I think the aromatic halogen bond acceptor, and also briefly talk about the importance of charge transfer in halogen bonding. And then lastly, the application of halogen bonding to fluorescent. So what is halogen bond? Is a non-covalent interaction occur between a halogen atom and a Lewis base. So interestingly, in this case, the terminology is halogen bond donor is actually acceptor of electron density, and the halogen bond acceptor is the donor electron density. So here are some simple example, like the boron interact with chloride anion, with ammonia, or even with the pipe type of bond. So this is ethylene here. The bond strength is, I would say, moderate compared to halogen bond, but I think, but very important is halogen bond you can tune easily as compared to halogen bond, because it's only have one type of donor, whereas in halogen bond, you can change from chlorine to bromine to iodine and so on. And another very important feature of a halogen bond is, like halogen bond, is have a linear geometry. So it's kind of ideal for supramolecular chemistry. And what is interesting is actually the linearity in halogen bond is significantly larger than in halogen bond. So what is the origin of halogen bond? I would say the most accepted kind of current model is this sigma hole model. So basically, if you have a thing of a halogen with 5 valence electron, when they form a sigma bond here, the electron density is pulled away. So along the C-axis here, so there's the diffusion of electron density. So that can readily reveal if you do a simple electrostatic potential map of a simple molecule like a methyl chloride, bromide, and iodine. So you can see here, the red color, the electron, which is correspond to the lone pair. But you can see at the end of the sigma bond axis here, you can see a bit of electron deficiency in chlorine and become larger in bromine and become very large in iodine. And so that is the reason why this sigma hole can interact with the electron donor to form a halogen bond in a linear manner. Again, this in terms of the trend for the different halogen atoms here, if you go down the periodic table, the halogen, the electronegativity will decrease, porosity will increase. So what you expect is actually iodine is the best halogen bond donor, followed by bromine, followed by chlorine, and fluorine is very reluctant to give up electron density. So very few examples of halogen bond involving fluorine. At the same time, you can, in the R group, so you can introduce electron withdrawing group. So they enhance the sigma hole. So that will actually increase the halogen bond donating ability. So that is kind of more electrostatic argument. We can actually use the simple MO theory to explain. In particular, I think you kind of needed that to explain the kind of charge transfer between the halogen bond here. So here we use a simple example, a methyl bromide. So the bromine is a halogen bond donor, and then the Lewis base in this case is just a water here. You can see here in terms of the molecular symmetry that can mix, but of course, whether there's strong interaction is depending on the energy gap between so-called the sigma star, the LUMO, and the HOMO of water. Now, when you introduce a halogen atom, so you can actually lower the LUMO. So like for iodine and bromine, now this is significantly low that, so there's the interaction here. So this, can basically explain the same thing in terms of the sigma star, the linear geometry, and in this case, as well as the charge transfer interaction as well. The geometrical feature of the halogen bond is highly directional, so roughly linear, and actually in many ways it's similar to a halogen bond. So instead you have halogen bond donor versus the halogen bond donor here. As I already mentioned before, I think the tunability is actually very important for halogen bond because you can change halogen atoms, so you can tune the halogen bond. And this is, the dimensionality is stronger in halogen bond than halogen bond. Okay, my interest was about 5 years ago in this topic is actually, firstly, later on I'll mention about, these fluorescent materials mostly are involving some aromatic acceptor. So now when you have halogen bond acceptor that involving a pi bond, like double bond or triple bond, is clearly, I think you interact at the center of the bond. But when you have a acceptor that is an aromatic system, that becomes unclear. So is it going to interact with the center of the ring or at the side, or we call it the rim? Okay, so that is the question need to be addressed. So that is the reason why I want to look at it first. Okay. Again, remember I mentioned about two ways to explain the halogen bond. If you take the electrostatic argument, the sigma hole, then now when you have a benzene ring, a simple aromatic compound with a benzene ring, then you all know the electron which is actually at the centroid here. One would expect that interaction will take place at the center of the ring. And also you have many other examples of aromatic interaction that's involving the center of the ring, like cation pi interaction, as well as so it goes CH pi interaction. Now, if we use the MO argument, so then basically you look at the HOMO and LUMO of benzene, and that's actually at the rim, so the sign at the center of the ring. Okay, so to answer this question, we did two things. One is actually go to the Cambridge physiological database because there's many structures that have a halogen bond. So there was a study back in 2010, but so we want to do an update study, and also specifically, I want to look at the aromatic interaction here. So this update survey involving particular the pi type and for aromatic contact. Now, in this case, when you have a benzene ring, there are three possible places you can actually interact. So either over the atom, or over between a bond, or over the centroid. So in this case, we borrow the coordination chemistry. So we call eta 1 for about atom, eta 2 about bond, and eta 6 about the centroid. So this is the result in graphical manner. Something quite surprisingly to us is actually when we do this update survey, the early survey suggests there's about 1/3 of the pi type of halogen bond interaction. But in our update survey, 2/3 of the interaction are involving aromatic halogen bond acceptor. And of the pi type, 96.5% are aromatic ring. And of this aromatic interaction, almost 99% are either 1 and either 2. So the interaction is actually over the atom or over the bond, not at the center of the ring. So we call it the rim specificity. These are the details, I won't talk about it. And so we do a kind of more systematic study on 10 kind of prototypical kind of aromatic system, 5 on hydrocarbon, 5 on nitrogen containing compound, and try to understand from computational what is the origin and where are the potential local energy minimum here. Now, as the interaction is maybe a bit weak, so we need to have to be carefully to scan the surface so that we can actually find all the local energy minimum. Of course, so we do a scan at the same time we actually do a full geometry optimization at omega B97 XT augmented CCP VTC. Okay, so in order for us to kind of have a good understanding of the interaction, we use the symmetry adaptive perturbation theory (SAPT), which is basically partition the interaction into electrostatic, exchange, induction, and dispersion. So how about to explain the interaction, why you prefer a particular site. So we use SAPT DFT method for this. So I just highlight one or two graphs of this. So this is a very fundamental system. It's the interaction of halogen bond system, in this case, just a chlorine 2, because I think you can do it with a high level theory with benzene. So when we do the potential energy scan, that show it's actually there's only one possible local energy minimum. So we actually have confirmed it with full optimization. So it's actually over the bond. The interaction with the centroid is actually not a stable equilibrium structure. It's a second order settle point. And if you do the SAPT scan, so what you notice is at the centroid, dispersion energy is the lowest as one would expect it. But at the rim, over the bond here, induction and electrostatic is actually the lowest. Okay, so with this, how do you explain? So obviously in this case, the answer is interaction with the aromatic system is actually at the rim, not at the centroid. In particular thing I mentioned about for aromatic interaction, mostly at the center of the ring, like cation pi, CX pi. So why in this case different from the other? So the explanation turned out to be actually quite simple. Because when you have a halogen atom, okay, so along the C-axis, so you have the sigma hole, so we will interact with the pi electron density or MO, but you also have the lone pair. So in this case, you actually have two other lone pairs. So these two other lone pair, which is perpendicular to the sigma hole, actually will repel the pi electron density. So this electron-electron repulsion is actually the largest when you put it at the center of the ring, because now you repel with all the p orbital or pi orbitals. But whereas it's over the bond, it actually is the least. So that explains why halogen bond have this kind of unique rim specificity. So we go on. I won't go through the detail of the scan. So now the actual local energy minima is shown in this red dot. So in benzene, there's only one interaction site. In toluene, there's two in the orthopolar position, and so on with naphthalene and anthracene and so on. So it's quite kind of unexpected. So it's only intact at a certain site of the aromatic ring, the same as all the nitrogen-containing compound. So this slide show all the calculated interaction energy in kcal per mole. So mostly they are in the range of 2 to 3 kcal per mole, which is quite significant, although it's less than halogen bond. But this can be increased depending on a lot of other factors. So in the case of pyro, I think you have a binding energy of about 3.29 kilojoule per mole. So here we use chlorine. And of course, I think when you change chlorine to bromine and iodine, what happened? I think we do one case. So the iodine will be stronger than bromine and chlorine. So that means this interaction energy could be about 4, 5, 6, 7 kcal per mole if you have iodine or some appropriate substitute. The point that is more interesting is, okay, in the case of benzene, the difference between the rim and the centroid is actually not very large, 0.6 kcal. But when you change to other type of halogen, this rim specificity is actually increased from 0.6 to 1.09 for Bl2 and 1.82 for Blf. That means in the case of we have something with iodine, there's no way that we actually interact with the center of the ring. So we'll be on a specific site. So this is the Van der Waals space filling model to show where the interaction. So in all cases, they happen in the rim, not at the centroid. Okay, so go back to the kind of popular argument using the electrostatic. If you do the electrostatic potential map for aromatic system, it's quite obvious it's always at the centroid. Because of the dispersion is large, so you have the largest amount of electron density over over the centroid. But you see none of the result, whether it's computational or whether it's actually from crystal structure, whether you actually find interaction over the centroid. Even in the crystal structure database, you can look at those cases where centroid is mainly because of symmetry, not because I think it is the preferred site. So go back. So how do you explain this list of interaction site? Now, then it becomes quite tricky because I think what you want to know is actually if you have a aromatic system, you want to know where's the interaction are. So as already explained, the alternate way to explain this is using the MO theory. So in this case, very simple, just homo-lumo. So that means in the case of aromatic, you just basically look at the homo. And because in the case of aromatic system, there's you generally have a degenerate homo. And also the homo minus one tend to be quite close in energy. So now this is the plot of the homo and the homo minus one. If you compare the interaction site, almost in all cases, except some minor changes, you can actually use the homo or homo minus one to explain the interaction site. That's actually quite nice. I don't think I have time to talk about. So you can actually use this to explain all cases. In some cases, I think you use the SAPD to help you to explain some kind of unique result. I probably just highlight two more cases. In Anthracene, you have free range. There's only 2 interaction sites. So the question is, okay, this is actually happening in the homo. But homo minus one, how come you don't see any of this? Because the homo minus one, there's a big difference, 1.3 EV. So the energy gap is larger. That's why you don't see any interaction site in here. The very interesting case is that actually is taurine. You have a taurine, so you have actually a methyl group, but if you put the homo, it's actually exactly like benzene. So you expect it's over the rim, but actually over the bond. But why become now over the atom? I think you will learn remember your organic chemistry about aromatic substitution. You know, when you introduce a methyl group, the charge polarization by the methyl group. So you actually now introduce charge polarization in the alpha and the para position. In this case, the alpha is minus 0.20, minus 0.1, whereas meta is small. So this charge obviously will help to stabilize the halogen bond. So in this case, quite nice. You can actually using this kind of concept to explain the sites of the interaction. I won't talk about the halogen case. It's exactly the kind of result. It's always in the rim, and you can use the homo right to almost explain everything. The electrostatic potential map doesn't explain this type of interaction. Okay. How about biological system? Because there are many biological systems have aromatic amino acid. So actually, there are actually tons of examples in the protein database. Here I just took 8 examples out of the PDB crystal structure. So this involving aromatic amino acids. So again, this example you can see here, phenylchlorine, bromine is already interaction in the rim. And again, so we just try to model the same thing. You check out the change of the amino acids and do a simple calculation. And again, this confirms the interaction site. Okay, so the take-home message, I think from what we learned here is actually the interaction with aromatic acceptor is site-specific. Now that is actually extremely important in terms of supramolecular chemistry because it's not interaction in any place aromatic range, not kind of fussy, it's only a specific site. So where exactly the site, you can actually do a simple calculation to calculate, but actually even easy, you can actually use homo minus one plus some other simple thing, you can actually even guess where is the interaction site. And again, the electrostatic argument failed to predict, where is the optimal interaction site. Very quickly on this topic again, is about using energy decomposition. Earlier on, I'll talk about SAPT, but I think there are a bunch of other energy decomposition method here. Here, I want to highlight one of the methods that is developed by Martin Gordon group here. It's a 2nd generation MO EDA. It's a diabetic absolute localized MO energy differential scheme. So the new feature of this scheme is actually, you can, usually when you do EDA, you just do single point energy, right? But in this case, you can actually calculate the geometry of that interaction by including a specific component here. So that's quite nice. So because the thing you can turn out, okay, if you include this component, what happened to the geometry here. So the Elmo EDA, basically there are three components: frozen, polarization, and charge transfer. The frozen actually make up of three parts: electrostatic, polarity exchange, repulsion, and dispersion. We chose this one because I think in the SAPD, everything lumped together as one term. Here you have specific polarization and charge transfer terms here. So basically you can just do optimization using the method using frozen, or including polarization, or finally including the charge transfer. So we actually explore all type of halogen bond. Specifically, we'll look at the aromatic one again, as well as I think the literature report, I think halogen bond involving radical and carbene are very favorable. So I go back to the kind of example I'll talk about, right? So let's look at some simple cases like single bond and triple bond, acetylene and ethylene. So you look at the acetylene here. So you just use the frozen. This is the interaction energy at -0.9. The geometry is 3.5. So everything is kind of underestimate. You include the polarization, the site improvement is still not correct. But when you include the charge transfer term, you look at this, the number is almost double. The interaction energy is about twice. And most important now, the geometry 2.79 is almost in excellent agreement in the case. It's the same thing for ethylene. In the case of the benzene, remember, well, I have shown calculation is over the bond rather than over the centroid here. Again, you use a simple, just a frozen the term here. You predicted this to be over the centroid. Even when you include the polarization, it's also got it wrong. But when you include the charge transfer, now the same thing you see, interaction is double. Now everything is right. Lastly, this example is quite important. Fluorine interaction with CLF. Now in this case, you can interact with the lone pair, which is the oxygen, or over the pi. Okay, so cut the long story short here. Now, if you just use the frozen or frozen polarization, you will predict it is over the lone pair rather than the pi. Only when you include the charge transfer, then you got it correctly. And this is in excellent agreement with the experimental result. Okay, so this here highlight the importance of charge transfers. So I only have a few minutes. I'll just talk about the application to fluorescent material here. Okay, so these are some of the early report 2011, 2013, but actually in the last few years, there are many examples of applying halogen bond to fluorescent material. But there's one kind of fundamental question. Almost all paper in the early paper, they say, okay, you introduce a bromine or iodine. So they basically claim that I think it's a spin coupling that would actually now enhance the intersystem crossing and then the fluorescent rate. So this is an example. I will skip the thing. You all know this very well here. So because of time, I'll go straight. So to answer that fundamental question, so we do a very simple system of an aldehyde, aromatic aldehyde, interact with BRF and IF. So we basically calculate the intersystem crossing rate from the single excess state to the triplet state. And in particular, looking at when you now interact with a halogen bond donor, what happened to this intersystem crossing rate? Okay, so very quickly, I think we use the Marcus equation to calculate the intersystem crossing rate. The fluorescent rate you calculate using water chill, this equation here. And most important is this spin optic coupling term. We're using the pi SCO method using a DFT approach to calculate. So this is the equation. Let me just have the last couple of minutes to give you the result here. Okay, so firstly, I think we need to know whether this is doing correctly just for benzaldehyde. So here is the intersystem crossing rate to calculate. The molecular orbital involved is actually the HOMO is the pi. The HOMO -1 is also pi. But the HOMO -2 is actually the lone pair. Okay, but the first accepted S1 is actually n to pi star. So the triplet state, there are two almost degenerate pi to pi star and n to pi star. So for just formaldehyde, so this is almost quasi-degenerate. So the inter-system crossing can happen to either T1 or T2. And you plug in those equations that I mentioned, we calculate, I think the number actually agree with the kind of experimental result. Something just to, again, to remind us that the LCA rule basically, if you now spin up the coupling involving a different orbital, then this coupling term will be large, the same one will be small. So they mean n to pi star in the singlet state to pi star. So you expect it to be very large, but small when you n to pi star to n to pi star. Okay, most important is the next two slides. So now we introduce a halogen bond donor, BRF or IF, and try to study the orbital energy change and calculate the intersystem crossing rate here. So the most important message is actually the halogen bond with the lone pair. Now, because when you get close, you actually form a halogen bond. So you actually will stabilize the lone pair orbitals. So the n to pi star now we would kind of in that sense will be destabilized. Whereas the pi star are not really involved in the halogen bond. So energetically it's being unchanged. So again, we will calculate the fluorescence rate here. So you will see the pi to pi star, in this case with the halogen bond, there's actually a slight increase, but the most important is the energy gap has changed. And we summarize with it in this diagram here, okay, because of time. So before interaction with the halogen bond system, so the intersystem crossing is actually to n to pi star singlet state down to a degenerate. So in this case, there's a fast intersystem crossing rate. So the fluorescence is mainly from singlet n to pi star to triplet n to pi star. When this interact, the formaldehyde interact with the halogen bond system, because of the stabilization by the halogen bond, the n to pi star now is raised. So same as the triplet and the singlet state. So now the difference is because of this change the orbital energy. So now in this case, involving a slower intersystem crossing rate. So in the case of halogen bond interaction, now the fluorescence actually occur from the singlet n to pi star to the triplet pi to pi star. So it actually change the orbital. It is still kind of explain the experimental observation to the rate. But I think there's one fundamental assumption everybody assume, I think need to be carefully examined, because they actually assume halogen bond will enhance the spin-orbit coupling or heavy data. But our calculation suggests is for a different reason why I think the fluorescence actually has changed the orbital type. And but we do actually predict that there's an increased fluorescence rate. Okay, I think I have to stop here, only 1 minute. So just me to finish. To acknowledge my research group. The people who I highlighted here are those all involving in the halogen bond project. The one in the middle is the one actually responsible, Anthracene. He's the one who doing all the calculation for this different project here. He actually just returned from MIT after finishing his postdoc. And lastly, I talked to a few participants here. It seems like very few of you have actually been to Singapore. So I just highlight to you, this is the kind of new icon of Singapore. You must come and visit. It's a kind of a very beautiful place. Thank you very much for your attention.
Thank you. Thank you. And maybe some question for this. Oh, we are going to go coffee break.
Yeah, may I have a question? Yeah. Thank you very much for your wonderful talk. For your last part is you speak too fast, so I couldn't really follow. So
yeah, okay. I'm sorry, I realized I ran out of time.
So your main point is that if you have a halogen bond, then spin-orbit coupling is a stronger, right? Or then spin-orbit or intersystem rate is becoming lower, even though spin-orbit coupling is large.
Okay, yeah, sorry, I apologize. I think I kind of skip a lot of my slide here. So the spin opposite coupling actually is small.
I see.
When the halogen bond is formed. So that is actually many papers that we have read, actually, they claim that I think the halogen bond enhanced fluorescence is because of the spin opposite coupling. But our calculations show that that is actually not the case. The enhancement is due to now the change of the now from the S1 to a different T1, which have enhanced, but the other one actually now become insignificant because the energy gap now N to pi star is become very large. It does not almost contribute anything to the fluorescence rate.